So I'm Pietro, I come from Italy, I'm from the academia, I'm not a programmer as profession. Although compared to the levels of people around me in the academia, I'm a relatively good programmer, let's say, because I work in a law department. So all this said, you might expect some very deep and philosophical explanation of a particular way to use pandas in the wrong way. This is not what I'm gonna show, because there are many, many different ways to use pandas the wrong way, and I will explore some of them. So pandas, I assume most of you at least heard about it, is this library for data manipulation, which I think is very good, but necessarily complex in some cases. So pandas has bugs, and many of them, unfortunately. You are very welcome to help fixing them. Occasionally, I'm able to contribute a bit, not as much as I would like. But, and if you are just scared by the pandas code base, but you would like to contribute, come talk to me. But this talk is not about pandas bugs. So I will not just bash specific bugs and say, oh, this doesn't work as we would expect. This talk is about design decisions which are not even necessarily wrong. They might be discussed, but often they are well justifiable. It is about a library, pandas, which seems very intuitive, at least assuming that you find NumPy intuitive. And I think NumPy is complicated, but is intuitive, because it allows you to do very complicated things in relatively simple ways. So pandas aims at the same level of intuitiveness, but it's not always possible to be as intuitive as NumPy. And I will show some examples of this. Enough talk, let's code. So I will really go by examples. Can you hear me? Okay. Starting with very basic examples. So if you coded a bit with pandas or even just with NumPy, you will find the first 5 minutes just boring. Hang on for the next. So let's start by creating a very stupid pandas object, which is a series of numbers from 0 to 9999. Okay, and we create a list with exactly the same content. Now you probably already know that this, that is, taking each element in the series with positional indexing. So I'm asking, give me element number 0, 1, 2, 3, etc. This is way less efficient than this. So we are talking about several orders of magnitude. Now you might expect this. Why? Because in general, pandas, NumPy, all libraries which are aimed to be vectorized, that is, at using at running operations on multiple elements at the same time, are bad when you look at single elements. You run operations on single elements. So this should not be too surprising if you even just use NumPy. We can do the same instead than looking at the single element, looking at slice with a single element. Again, the difference is huge. Probably many of you know about time limit. If you don't know it, well, it's pretty evident. It's used to to benchmark some specific parts of code. I didn't talk about this. It's just saying don't run many repetitions of this code, just try it once. And I'm doing this to avoid caching, which is present in pandas. So trust me, this is just a reasonable measure of the difference between the two lines of code. And you see this is way slower than this, and this is way slower than this, okay? But this should not be surprising. Again, pandas has a lot of checks, a lot of layers of code compared to a simple Python list. However, although the problem is present also in NumPy, in pandas it's much worse. So for comparison, if we take a NumPy array with exactly the same content and take the difference, now the difference is relevant, it's basically a factor of 2, but it's not by far as relevant as with pandas. Now you might say, well, we are cheating, we are comparing lists and series, but series are really not optimized for I mean, it can be used for positional indexing, so give me the fifth element, but they shine at location, or at label-based indexing. So give me label 2, 3, and 6. Okay, let's look at label-based indexing, which then we compare with a dictionary, because in both cases, it's, I mean, a series is perfectly equivalent to a dictionary in the sense of label, of finding keys and associated values. And still, the difference is huge. So, long story short, if you are using pandas to do any kind of operation, element by element, it's not the best use. And if you're using pandas only for this, then you should just replace it with dictionaries and lists. Now, it sometimes happens to me that I need to do some operation element by element, but pandas is just so handy for loading data, saving data, passing around data. What I typically do is I load an object with pandas, I make a dictionary out of it, I run my operation, and then I dump it back in pandas and save it. So pandas can still be useful for input-output, but don't run operation single elements because it's a waste of time. Okay, let's move to one of the nicest features of pandas, clearly, since it does label-based indexing, which is indexes. Now, pandas, a bit like Python in general, allows you to do several things that you really don't want to do, or you want to do as less as possible. And one of these is duplicated indexes. So let's create a stupid data frame, which is just a table full of random numbers, okay, with seven columns. And now we create another data frame, which is made of the concatenation of the two, but we drop the first 50 elements. You'll see why, okay? Now, this index is not unique because we concatenated the two data frames and each had numbers from 0 to 100, okay? So it's not a unique, it's not even monotonic because numbers go from 50 to 99 and then start again. This is ugly. Again, it can happen because maybe you load some data which has a structure, but you want to change this as soon as possible. So this data frame ends with numbers from 95 to 99, as you expect. The first row is just, 7 random numbers. And we can change it to numbers from 0 to 6. Now, you might expect to want to do this also, sorry, mistake. This is not the first row. This is the row indexed by 0, okay? Because this is label-based indexing. So this is working like a dictionary. So this works. We just took the line corresponding to the 0 label and we changed it to range 7. This breaks. And why? Well, because of the way of how we structure the data frame, this is actually 2 lines because the key is repeated. And so we cannot assign 7 values to these 2 lines of 7 values each. Now, we can obviously reset the index, which basically means that now the index goes from 0 to the number of elements minus 1, 149. This index is unique, this index is monotonic, this index is cool. It's basically an index. And this time, we can do the same thing, but it's gonna obviously lose the original associations of keys to values. Now, let's run some comparison. If we use label-based indexing, okay, so we are looking for a given label, for instance, from 0 to 50. In the reset index, so the index with the unique index, it takes more or less 7.5 milliseconds. It takes more in the non-unique index. We can also check this with another range of values, and again, the non-unique index is way slower. And this, well, this is a fluke, but trust me, in general, non-unique indexes are less efficient. So again, let me stress, you can have non-unique indexes. Sometimes it's legitimate because of how you construct the data, but as soon as possible, you just remove these characteristics. Okay, another thing that pandas allows us to do, and is not necessarily always good, is to append elements to an index. So you maybe remember that this data frame ended with 99. We can add another line, and pandas trusted us. We know what you're doing. It just added a new line. Now, this is not trivial, because if you compare with NumPy, in NumPy, if you have a matrix, so a vector, a two-dimensional array, and yeah, this is the last line. If you try to add another line, it will just complain. So pandas is more flexible, it's nicer to you. Okay, I trust you, you know what you're doing. But this is not always good. I mean, you should know what you're doing. So let's take this example. We're taking a stupid series, and we are appending 1,000 elements, which are really stupid. They're just the label times 2, okay? This takes 400 milliseconds. Now, just making this change, that is, telling it before I'm gonna wanna have this index, makes a huge change in terms of performance, from 400 milliseconds to 67. So in general, you don't want to append multiple elements to a series or even a data frame. It can happen, but most often you should be able to already specify the intended index in the beginning, or to just build a list with the results and then transform it into a series. Now, notice that this is really a problem of appending. That is, now I'm appending a new element at position 202, at label 202, but replacing it is pretty fast. So the problem is really what I told you, appending. And yeah, same thing. I add 2003, it's slow. I replace it, it's fast. So in general, as the series and data frames should be as static as possible in terms of structure. Okay. This is a problem that probably many of you, if you use pandas for a while, faced. But the consequences are maybe more nasty than one would expect. So what is concatenated assignment? Let's take a stupid data frame again. It's just full of missing values. It has 5 columns and 5 rows. Concatenated assignment is this. Sorry, this is not assignment. We are just taking the third row, the first column. Fine. This is concatenated assignment. We use this to do another assignment on it, okay? So this is concatenated because this returns an object, the pandas object, and this again. Now this is bad because you never know if this is a copy of the original data or a view, in the sense that pandas tries to be smart and does not always does not always do what you expect, unless you're way smarter than pandas, which given the complexity of the code base is not always trivial. Now, this will work in the sense that it does what we want, but this won't. So the only difference is that here I look at 2 indices, here I look at the slide, and then a slightly more complicated indexing. So in principle, it's actually the same. I'm using lock to get a new object, and I'm using lock again on that object with a value. But it works differently. So this had no effect at all. Now, pandas is nice because it's giving you a warning. It's saying, hey, what you're doing may or may not work. So you see the warning, you say, okay, well, I should check what I'm doing. More worrying to me is that when I do this, I might be tempted to say this is just a regular object. And so when I do this, I might forget that I'm actually modifying the original data frame. And I'm actually modifying the original data frame. So in some cases, concatenated assignment works, and it's not what I might expect. Maybe because my idea was just to work on this rather than on this. The solution is always the same. To be on the safe side, you take a copy of the object. So once you take a copy, it's no more a view. It's actually a legitimate object. Okay. Another very nice thing of pandas, and in particular of data frames, is the ability to manage different dtypes, which is not there again in NumPy. In NumPy, each array has one dtype, possibly object, but one dtype. So one type of data. Pandas is more flexible in this aspect too, but again, this can bite you in unexpected ways. So let's take a data frame which for now has no columns, okay? Only an index made of 10,000 elements. And let's fill it. Now we are doing everything well. We're taking a copy, so we are not disturbing the original data frame. And then we just add a column, which again is index times 2. Okay. Now we do exactly the same operation, but instead of doing it all at once, we do it in a loop. So for every index in the index of the data frame, I'm going to put in the column A at that label the value times 2. So exactly the same. We've already seen that loops are bad, right? So this is bad in terms of performance. That's it. We are warned. What we might not expect is that there is a difference in terms of result, okay? Not just of performance. So this took more time, but it also gives us a different result in the sense that these are really floating point numbers. What happened? Now, let's come back to the F. The F was just the empty data frame, okay, with no columns. If I add a single element in that data frame, what happens is that this was an integer, but since I gave no value for all the other rows, the only way pandas has to manage this, given that integer numbers don't have missing values neither in pandas nor in NumPy. The only way to manage this is to transform the column in a floating point column. And this really comes out often if you just plug integer numbers in otherwise empty lines, columns, and is usually annoying. There's a simple solution to that. You just take a value which you assume you won't find in your real data. You pre-assign the column, and then you can do whatever you want element by element. So by doing that, we get indeed, it's slow because we know this, but at least the result A is good. B is the previous one, which was wrong. So in general, beware that integer don't play well with missing values. Okay. Still about D-types, in particular about casting from one D-type to the other. So let's consider this, again, pretty ugly data frame. It's just 2 rows, 1,000 columns, initialized to -1. So again, we are going to put integer numbers in it, so we want to initialize this to -1, so we have no surprises. Now, the D-types obviously are all integers. That's good. Now, this is a stupid method, but assume it's not so stupid. So assume we have some external functions returning some result for every I. And it returns a Boolean result. Now, here what we do is, again, I'm not trying to convince you this is smart, but we take all the values and we add the Boolean value, okay? So whether the specific column has an odd or even label. Here we do something in principle simpler. That is, we just take this value. We are not adding the previous value. Okay? Now, this takes 200 something milliseconds. This takes way longer. 3 times longer. So again, here we are adding and then setting the value. Here we are only setting the value. Why is this slower? Well, this is the reason. This did exactly what we expected. That is, when the column is even, it added 1, and otherwise it added 0. But this didn't. Because I asked pandas to just place a Boolean object in the column, and not only it actually placed the Boolean object, but in order to do so, it needed to change all the types to object. So what happened is that pandas changed, trying to be nice with me, because I asked pandas to place Boolean object in it, it changed the type of all of them. And this is, we will see in the next notebook, a costly operation. Okay, I told you pandas is able to manage multiple types and that this is nice. In particular, pandas is able to manage multiple types in independent columns of data frames, not rows. So this is not trivial. You can have, as I will show you here, several columns with several types, but not rows. Okay, again, stupid data frame, empty data frame with a stupid, very short index, okay? Now what we do is we add 5,000 columns, one at a time, and they are pretty similar to what we saw before. So this is how it looks. Before they were just 1 and -1. Here they correspond to the label of the column. How much does it take? Maybe I could have picked a lower number, but trust me, it's not so long. Okay, 1 second and 1 second point 4. Now, as I told you, this is bad because we are adding columns one at a time. So let's be smart. Let's pre-allocate the index. So now it knows the range. Okay, I already told in the previous example that the index is range 2. But now let's also inform pandas that I'm gonna want to store 5,000 columns. That's smart, right? So it should be quicker. And instead, it's not. Wow, exactly the same time. It's okay, it can be also worse. Now, anyway, I had promised you, this is a risk of running live, live code, but I think it's worth it. So anyway, we would have expected this to be better because we pre-allocated the columns. So what's happening? We can get some use of a couple of pictures. So this is how a data frame looks on the outside. You just have the values, the index, the columns, right? Pretty simple. But this is how it actually looks on the inside. So the values, which can have multiple data types, are organized by blocks, each block corresponding to a data type. So for instance, if I have 2 integer columns, they actually are regrouped together in a single column, which in the end will be represented by a single NumPy array. And this is valid also for float columns and object columns. So what happens is that, and we will see it now step by step, is that when I pre-allocate this data frame, it is obviously all integer type. Oh, sorry. So here I did not just pre-allocate the index and columns, I actually fill the values. And it takes a bit less than 400 milliseconds. If I pre-allocate it with a float value, it's going to take quite a bit more. So what is happening? The fact that here I told it in advance there are 5,000 columns, but I didn't tell it what would go inside, meant that pandas thought, okay, it's going to probably be a floating point value. Anyway, since I have no value, I need to put a missing value inside. So that's going to be a float type. Here, since I told it -1, it already knows it's an integer. It's much quicker. Now, when it actually starts from floats, so it's not really just a problem of missing value, it's a problem of having the wrong data type. What happens is that, and I'm going to show now bit by bit, initially I have this 5,000 columns, all of float type. Then I set the first column, which is exactly the first step of what I was doing in my loop, okay? I set the first column to 0, 0, which are integer numbers. So pandas has taken the float block and has reduced it to only 4,000 something columns and has added an integer block, which for now has only 1 column. Then I go on, second column. Pandas has actually created another integer block. So maybe I lied you because I told you that pandas would put together all the columns of the same type in a single block. Now the thing is that this operation of putting all the columns of the single type in a single block is costly. It's computationally expensive because it means relocating memory. So pandas will avoid it as long as possible. So I go on adding columns, and again, pandas is adding new blocks. Cool. And indeed, I can check that pandas know this is not good in the sense that this data frame is not consolidated. There is more than one block per d-type. Now, if I run more or less any kind of meaningful operation on this, like taking the maximum, which just returns what we expect, then we see that the blocks have been consolidated in just one. But how this happens tries to be smart. It's not always what you expect. Indeed, now data is consolidated. So if we take the following, that is, we add columns one by one, and every time we take the maximum, it should be less expensive than adding all the columns and then taking the maximum 1,000 times, as stupid as it may seem. Actually, it's not going to be what we find. So the first, which is taking only partial maxima, is less efficient than the second. For the reason I just told you, consolidation is expensive. Yeah, I already showed you that as long as we have no casting, there is no problem. I'll try to speed up a bit. Okay. Data frames have axes on dimensions, and in principle, we might tend to say that, yeah, we call one column one index, but they are actually exactly the same. The fact that the types go by column makes this not exactly true. So let's take not necessarily very nice, but legitimate data frame, because it has several d types on several columns. This happens often, like in economic data I work with. So the d types make sense. There is an integer, then the float column. This is object because pandas basically does not know about fixed length strings, and then strings are just objects, and another integer. Now, if we take the mean, pandas is smart enough to know that it can take the mean of an integer column, it can take a mean of a float column, it can take a mean of the other integer column, but there's no way to take a mean of a string column. Good. If we take the mean on the axis, on the other axis, again, on every row, it's going to take the mean of the three values of which it makes sense to take the mean, and it will just discard the string column, and this is also good. Now, we might expect that if we transpose the data frame and then take the mean, which is, it's implicit, but it's a mean on axis 0, it's actually the same of taking the mean on axis 1, right? Wrong. Why? Because, again, this is just for clarity, it's useless. When we transpose and take the mean, what happens that everything has become an object. Because we can allow for different d types on different columns, but not on different rows of the same column. So this data frame transposed can only be considered as an all object data frame. And hence, when we then take the mean, there is nothing left to take the mean of. Okay. Pandas is very good at group by operations, in the sense that it's pretty efficient when you actually have a group by object. It's doing something smart. It's just taking, recording the positions of the groups, and it's actually not moving data in memory. Still, it can be inefficient if you want it to. Okay, so let's take, so this is a quite trivial data frame of stock market prices in which you have a time, the kind of stock being traded, a bid and an ask prices. The interpretation is not particularly interesting for us now. Now, the typical use of group by is then to call apply on it and then some function. Now here I'm just using for simplicity and the mean. Usually if you use apply, you probably, I mean, this could have been replaced by this, which is quicker. But in principle, you might want to have any kind of strange operation happening group by group. And apply just works, okay? It just took groups by the name of the ticker and took the mean of the values it could take means of. However, did we do this in the best possible way? So this apply operation took 90 milliseconds. If we had used aggregate, which is different than apply in the sense that is specifically targeted to aggregating groups in single numbers, one per column, it would have been massively faster. So apply is smart in the sense that it always tries to do what you want to do. But this cleverness comes at a big computational cost. So if you know what you want to do, and if you know this operation is called aggregate, that is applying operations column by column of each group, then use aggregate. Vice versa, in some cases you want to do a transform, that is operate element by element, for instance. And again, this is the right way to proceed. So applied is more powerful than aggregate and transform together in the sense that it does other things. But if what you want to do fits either in the aggregate or in the transform case, you'd better use the right function for it. Okay. Since I don't have much time, I must decide what to skip. Okay, this is particularly nasty. Now, here I'm creating a stupid data frame with 1,000 columns, 100 rows, and sending it to disk, okay? So just that I can use it later. Now, assume I'm interested only in the first four columns. So I'm smart. I don't want to load the entire database in memory at once. I'm just going to load a chunk by chunk, and then just keep the columns I'm interested in, okay? In this way, I will get the same result I would have got by loading the data frame and taking the first four columns, but without using memory for all the data frame. Now, what's the problem? That if I do this, yeah, each of my chunks has exactly the shape I expected now. That is 10 rows because this is the size of a chunk, and 4 columns because it's what I wanted to keep. The problem is that the array below my columns is still the original one. Why? Because again, pandas tries as much as possible to not copy data around, and hence when I did this, the actual data remained the same, and I just got a new view over it. So this is smart only if you do this. Otherwise, it will just complicate your code. Okay, there's still a bit of time. Let's look at multi-indexes because I love them. They are a very powerful feature of pandas. So, how much time? Okay, cool. Good. So we create a pretty stupid data frame, but it's slightly less stupid than other stupid data frame in this presentation because it has a multi-index, so 2 levels. And the columns are just a regular index. Now, what's going to happen if I ask for 1, 4? Now, you might tend to say, well, this is 1, 4. It's the first line of the index. Or you might tend to say, this is 1 and then column 4. Now, pandas is pretty consistent in favoring the multi-index interpretation, so it's going to give me the first row, and it's nice to know. Still, it can be nicer to be explicit. So this is an explicit way to write this, an ambiguous way. Because if instead you want to get indeed the first, so label 1 on the first axis and label 4 on the column axis, you would have done this. So this is a partial key, and this is the columns I want. Now, one very important thing to stress is that I didn't use tuples here by chance. Usually in Python, we are used to think that lists and tuple are exactly the same thing, except for implementation details, like I can append to a list, I can insert into a list, but it's less efficient. In pandas, they are not the same thing. This is going to work. It means look at 1, 6, and then 4. So look at 1, 6, and then 4. This is going to work differently because it actually means look at 1 and 6, which is not present in the first level, and then 4. So it still does something totally meaningful. It's just different than this. This is going to fail because it means look at 1, 2 in the multi-index. But 1, 2 is not in the multi-index, so it's going to fail. You might hate this, but after a bit you're going to love it. Because once you follow the convention, it's very clear, it's always expected, it also gives clarity to your code, and pandas is consistent. But you must be aware of it. Next notebook, do you have time?
we'd better go to
Okay,
questions.
let's go to
because
questions.
only 5 minutes left.
That's fine. The last ones were really not interesting, as you might figure. Okay, questions.
Thank you very much for your presentation. I want to conclude it in one sentence. And if you want to use pandas efficiently and without stupid errors, know the underlying data structure, both pandas and NumPy arrays, and tuples as well. So, any questions?
Yeah.
Oh.
You mentioned about that when we transpose data frame, we have all the types changed to object. I didn't fully understand that.
Okay, it's not a general statement. The problem is, if you have a data frame with different d-types, the different d-types are so each column has an associated d-type. And this is fine because pandas knows how to manage different d-types on different columns. When you transpose the data frame, in principle, you have one d-type associated to each row. But pandas is not able to manage different d-types on different rows. So the only thing it can do if it has multiple d-types is to transform them to objects. But if you started from a all float data frame and you transpose, it's still an all float data frame. And if you started from a mixed integer float data frame, pandas is not going to cast to object, but just to float, because it's enough. But if you have strings in some columns and you transpose, then the only thing that pandas can do is to transform it all to object, because there is no other data type which on a given column can store integers and strings together. So it's just a problem if you have different data types on different columns. Now, usually, if you have different data types on different columns, transposing is not something particularly meaningful, but still it can happen. I mean, it happened to me. Maybe I'm just too nasty.
Thank you.
Here you made a distinction between indexing with tuples and lists. Could you index it by a list of tuples?
Absolutely. So let's take this example where we have a multi-index on the index axis. So a list with tuples means a collection of keys. Each key is a tuple. So for instance, a list with, maybe it's better if I show. So a list I could do. First, let's say we want the fourth column, and then we want 1, 4, and 2, 5. It's just taking 1, 4, and 2, 5 on the index, and then column 4. I could also have maybe I'm talking too fast. I'm thinking about a list, a tuple of lists. It could work. I'm not sure. Let's experiment. We could have this. Yeah. Okay. We can also have a tuple of lists, which means, so since this is a one element tuple, it means we want to look at the first level only, and then on that level, we want to look at 1 and 2. And it's doing exactly what we expected. So I was afraid this would be supported, but the logic is perfectly coherent. Maybe not so immediate, but coherent. Basically, tuples go horizontally in the axis, lists go vertically in the axis, and this is working as it should. I don't know if we expected that, but it works as it should.
Thank you.
You're welcome.
Any more questions? Okay.
Can you please explain why is group by aggregate mean construction is dramatically slower than group by aggregate construction?
Sorry, can you repeat?
Why is group by apply mean construction?
Okay.
Да, slower
Okay.
than group by
Okay.
aggregate construction.
So what happens if you do aggregate? You're doing a very precise operation, which take each group and for each column take out one value. Which value will depend on your code, but the end result has a very expected structure. One value per column per group. If you run apply, you're just saying pandas, I will do some operation on each group. You have no idea what's gonna come out from here, so you have to find out. So what actually pandas does is, it first runs on the first group. It looks at the result. It tries to infer, first, what kind of result is it? Second, what kind of structure will all the collection of results have? So for instance, the result of the group by operation will be a data frame, a series, a data frame with a different columns. So it has to figure out what actually you're returning, and this takes a lot of time.
So is it because additional operations for each group and for very big data frame, it's not matter?
Good question.
If
So
you have a very big group, then additional operation is not very much. No,
okay, good question. To be honest, I'm not sure of the answer. I would say that for a very large group, the difference should be minor. But I would say that even for a large data frame with small groups, with relatively small groups, the difference will be present. So the difference could disappear with the size of the groups, but not necessarily with the number of the groups. But I should test this, I don't know.
Okay, thanks.
You're welcome.